Okay, lecture 5 on systems of linear differential equations. So we had x prime, y prime, and a1, x, y, and this is a. Remember, determinant a minus lambda y 0, and that gives me eigenvalues lambda 1 and lambda 2 and eigenvectors v1 and v2. Now I discussed the case that lambda 1 and lambda 2 are real and distinct. So case 2 will be case 2 complex eigenvalues. So lambda 1 and lambda 2 will be like this. Lambda 1, lambda 2 will be alpha plus minus beta I. And the v1, v2 will be something like this. And the v1, v2 will be something like the same. A, B, and plus minus C, D, I. Okay? So, let's assume that the plus here is for the plus, that doesn't make too much difference. So, we have these two solutions. Remember, the solutions were like this. So, say xy number 1 was this. E to power alpha plus beta. Okay. Let's expand this and see what we get. Well, this guy here is, so I have this V1, say, let me just write V1 here, that's the V1. And then I have e to power alpha, e to power I, beta. So that is V1. Let's just write e to power alpha, just a real number. So I have cosine beta plus I sine beta. Okay? So the first one, xy1, will be this times this. So let me erase that and write it here. So it will be something like this. I have e to power alpha, say, times a b plus c d I times cosine beta I sine beta. Okay, so let's see, e to power alpha is just there. Now this one times this one is it will give me, that's real, so let's just write the real ones here. So our real ones are this thing, a, b, cosine beta. This I times I is -1, so this time this is also real. So I have minus CD sine beta. So this is the real part of this expression here. The imaginary part is this time this, and this time this we have imaginary. So plus, so this will, it will be this times this, which is A, B, sine beta, and this times this, C, D, cosine beta, I. Okay? So, that is the case that I chose, plus and plus. Now you might say, well, how do you know that alpha plus beta I corresponds to AV plus CBI? That's okay, this might be negative. Just put the plus here and put negatives here. Okay, so you can always write plus and throw the negatives inside that matrix. Okay, anyway, so you will see that it doesn't make any difference which one comes first. So this is, say, the one which goes with alpha plus beta. Now, let's find the second one. The second one will be 2. What happens here? So the second one will be the minus with the minus here. Minus with minus here. Okay. So what happens? Let's see. So I have a minus here, a minus here, a minus here. The same thing happens. So this e to power minus beta I is cosine beta plus I sine minus beta. So that's cosine minus beta I sine minus beta. Cosine minus beta is cosine beta. Sine minus beta is minus sine beta. So this e to power minus beta I is this. So let's see. This time this is this guy here. Plus plus minus minus is plus. I squared is negative. That's correct. So this one is here. Then the i's. So this one times this one is here. This one times this one is here, but both of them are negative. So I just get the negative here. Okay, so this is the second one. As you see, the difference between this one and the first one is simply right here, plus minus. Right? So the first one was plus, the second one is minus. So we know, in fact, we can prove this fact that if I have a complex solution, then both real part and imaginary part separately satisfy the equation. Which makes sense, because when you plug in this whole thing, then you will get the real part and an imaginary part. And if that's equal to 0, say, if you just throw them on one side, then the real part should be 0 and the imaginary part should be 0, separately. And the real part comes from this, and the imaginary part comes from this. So this satisfies that, and the other one also satisfies that separately. So they separately give me, say, solutions to the system without the I. I don't need the I. So, okay. So why should I go with this long? In fact, what you see here, this, the first one is the linear combination of this and this. The second one is also linear combination of this and this. So why not just picking them, choosing them as solutions, not a linear combination of them. So I will choose them as solutions. So let me erase this. Say the solutions number 1. Let's just pick this one. So that is A, B, cosine beta minus C, D, sine beta. And you can tell that this is in fact this. A, B, C, D. Cosine beta minus sine beta. I personally prefer minus cosine and sine. So, but anyway, let me write it down and you will see what I'm saying. So that's cosine beta and minus sine beta, right? Remember when you multiply this matrix by this vector, it is like this times the first column plus or minus this one times the second column, right? So I just wrote it down in this form. And the second one, you can see that the second one is also amazingly nice. And so the second one is, again, it's right here. I can write it as A, B, C, D times, oh gee, I forgot one thing. You didn't tell me, that is the e to the power alpha, right? E to the power alpha. So just write it. And if I forgot the e to the power alpha, please write it. And don't forget the e to the power alpha anyway. So this will be this thing times sine beta and the cosine beta and times e to the power alpha. So I'm not sure if I dropped that. Okay, so the two solutions are these two. Now I personally prefer cosine to be negative, but you can either write it like this or you can write it like that. Let me grab another color here. Or maybe in my, I posted some notes, maybe I chose this, which doesn't make any difference because you're it's the same thing because you are multiplying this by a constant, okay? So this comes with a constant, and the constant, if it's positive, then you make it negative or something like that. So it comes with a constant, so the solution will be something like this. xy, in fact, the complementary solution is the xy, which is some constant times the first one, plus another constant times the second one. Right? So it is some constant times this one. I might forget that. So no, the first one was this. Or which one is the first one? Okay, I took this one to the first one. So A, B, C, D. Let me choose this. Minus cosine beta, sine beta, minus cosine beta, sine beta. Oh, gee, I forgot the e to power alpha. Close. C2, A, B. No. A, B, A, C, B, D, sorry. A, C, B, D. A, C, that's what it is. Whatever it be. A, C, B, D. A, C, B, D. And that was sine beta, cosine beta, e to the power. Okay? So that is the complementary solution. Now, what does this mean? This let me open this thing and oh gee, I forgot one thing which you missed. They all have T. T. T, 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 T. Oh, not the T. Really? No. So all of them have T. So beta T, alpha T. Okay, so don't forget that T. Okay. So yeah. So let me write this, let me keep this and then write it here again separately. So the x and the y separately. So x will be C1 and that is A minus A cosine beta t plus C sine beta t and plus C2 and the whole thing plus C2A sine beta t plus C cosine beta t e to the power of t. Okay. So this is x as a function of time. X as a function of time, and y will be okay. So y will be the second row. It is b c1 b minus that's minus cosine beta t minus b cosine beta t minus plus d sine beta t plus c2 a b c sine beta t plus d cosine beta t e to the power of t. So as you see, the x and the y are in fact functions of time. So what I have found is basically parametric equations of some motion. Parametric equations of motion of, say, a particle, and depending on the situation, you will get something like this. If you graph them, and I have some graphs for you, so they go like this. They're like spirals, and also the other way, in all ways. So if it goes this way, it measures it's kind of just going to infinity, right? And this happens, we can tell that this happens if alpha is positive. Otherwise, these are just A, B, C, D, A, B, C, D are constants that we will find, constants, and the C1, C2 also constants based on initial conditions. So the thing that gives you a solution that goes to infinity is this, the e to the power alpha t. So that if alpha is positive, then it goes just boom, boom. And if alpha is negative, then it goes this way. So positive, it goes this way and gets larger and larger. And if you graph each one of them separately, if you graph each one separately as a function of time, well, you see something like this. So if alpha is negative, you can see if alpha is negative, this gets killed. So you will get something like this, right? So that x t, if alpha is negative, looks like this. And y too, y will be something else, I'm not saying, but it is like a sinusoidal, say, shape that dies. And if alpha is positive, it goes up, and just the system just collapses. So these are streamlines, which are in fact, if the particle is moving, given the x and y coordinates of the particle in plane, given the x and y coordinates in this form, then that particle, depending on that e to the power alpha t, depending on alpha, is either, if alpha is positive, this particle just going round and just goes back. Otherwise, if this particle is, if alpha is less than 0, negative, so it goes like this, boom, 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 until it gets killed or reaches 0. Well, theoretically, it never reaches 0. That's like the limit, Limit is you never reach that point, but you get closer and closer to the point. So, this is an analysis of this case. So let me see if I can come up with a nice example for you. I can take a look at examples in the book with nice solutions. Be quick. So, I'm not sure, but let me just pick one of them. So this one is x prime, y prime example. I can write it here and see if it is x prime, y prime is 2 minus 5, 2 minus 5, 1 minus 2. Negative positive 1, so and x y. Okay, let's find eigenvalues. Determinant of a minus lambda I is 2 minus lambda minus 5, 1 minus 2 minus lambda. So that is 2 minus lambda times minus 2 minus lambda plus 5, 0. And this is, well, I'm going to write on top 1 minus 2, and this minus, this is minus plus 2. Is it? Yeah, okay. So I have y squared minus 4 y squared minus 4 plus 5. See, I don't want this to have okay, so equal to 0. That's right. So we have y, lambda is minus 1, lambda squared. So lambda is plus minus half. Well, I don't know this thing. Let me see what can I change here so I will get a lambda here. So if I change this to plus 3, then I will get, let me see if I write plus 3 here, then I have lambda squared plus lambda plus 5. That is 1 minus, I think that's much better. So let's try this. Let's try this. So which one was that? Lambda plus 3. Okay, so this will be minus 3. Yes. So let's see. I just. In fact, the other one is also nice because that's a very special case. Plus 5. I will discuss that after this one if I have time tonight. So that's y minus 2, lambda plus 3 plus 5. So I have lambda squared plus lambda, plus minus 6 plus 5. I wanted this to be 4. If I have 4, that's 1 minus 5. Yeah. How can I get 4 here? So if I have 10 here, right? If I have 10 here, 10 minus 6 is, no, I need 5. So if I have 11 here, right? So I need 11 here. Because the other one, if that's minus 1, it has a real solutions. I need the complex solution. So if I have minus 11, then this is plus 5. Yeah. So I need plus 5 here. So what's going to do? 11. I can write 11. Let's try. It's a good practice to cook some problem which so lambda squared minus that's plus lambda minus 6, say plus 11, that's lambda squared plus lambda plus 5 equal to 0, and lambda will be minus 1 plus minus okay, that is 1 minus 20. I guess I am just making this even more difficult. So let's see. If I need 5 here, I can get 5 here. Okay, I made this. I made this big mess. So that's okay. Just let's be this thing. I should have written this down, and I should have come up with some nice numbers that would give me nice solutions. But anyway, this is okay. So the solutions, the lambdas are lambda 1 and 2 are minus 1/2 plus minus square root of 19 over 2i. Let me double check. So lambda squared plus lambda minus 6 plus 11. Yeah, I want about that. Okay, so I think there are 2 here, but anyway, so that is 4 times 5, 20. So 1 minus 20, that is minus 19. And so I have these two. Let's find eigenvectors. I will find one of them, and the other one is simply the. So let's see. Eigenvector number 1. I just use one of them, so it is 2 minus. Let's take the positive one. Minus 1/2 plus square root of 19 over 2i times v1 minus 5 v2 is 0. Remember what I'm solving is this. I'm solving 2 minus lambda minus 5, 1 minus 3 minus lambda times v1, v2 is 0, right? And I said, because I set the determinant to 0, it means that the second row is a linear multiple of this, multiple of the first one. So let's just get rid of the second one, and I wrote down the first one with lambda being minus 1/2 plus with the plus 1. Okay, so that's what I did here, and so if I set v1 to be, let me simplify this thing, 2 plus 1/2, that is 5 over 2 minus the square root of 19 over 2i times v1, and that equals 5 v2. So if I choose this to be 10, I can take this to be 10, right? So let's say v1 is 10. So if v1 is 10, then what do I get? I will get this thing divided by 5 times 10. So this divided by 5 will give me 10 here, 10 here. And so this gives me 10. If it is 10 here, then I have 5 minus square root of 19i. Yeah, if you just divide by 5 without take this to be 1, then this will be 5 over 10 minus square root of 19 over 10. Okay, so now with what I had in mind, I mean the way that I wrote down the equation was this. So I said this positive goes with positive. So the eigenvector is, let's take this, 10, 5. I said plus goes with plus. So if I write plus here, I have 0 here, and minus square root of 19 I. Okay? So with plus goes this. And then that A, B, C, D was what? A, B, C, D was this thing, right? A, B, C, D was this. And what is alpha? Alpha is minus 1/2, and beta is square root of 19 over 2. Okay? And A, B, C, D, A, B, C, D, the way that I designed that to be this positive goes with positive, since that was that eigenvector is the one for positive eigenvalue, so I put positive here and negative inside. So the A, B, C, D will be this: 10, 5, 0, minus square root of 19. Okay? So the solutions will be, what was that? I forgot. So solutions will be x, y was C1 times AC, which one was that? One was minus cosine, sine, the other was one sine, cosine, minus cosine, so it will be, what will we write it first? You can write it like this, that's okay, you don't have to expand it. Oops, beta, what is beta here? Beta will be square root of 19 over 2t sine square root of 19 over 2t plus C2 10, 0, 5 minus, it will be, remember the first one was sine square root of 19 over 2 t cosine square root of 19 over 2t, and this whole thing is multiplied by e to the power minus 1/2 t. So that is the solution. You can leave it like this, that's okay. You don't have to multiply. Okay? So, the way that I wrote it down was with the plus, I picked plus something. That's why I put minus square root of 19 here. But anyway, I guess even if I put plus, I'm not sure what happens. Maybe no, I will check it. You can check and see what difference it makes. Because of these constants, maybe it doesn't make any difference which one goes here. So either 0 plus or 0 minus doesn't make any difference. So that's the general, the complementary solution when we have two complex eigenvalues. Now, let me find another one in the book. Does it have? Oh, okay. So, let me do another one for you, and then the other situation, and I'm not going to talk about that too much. So, another example, and this is from the book. And it is x, y, prime is x prime, y prime. Did I put prime? in the other one? Sure. Minus 1 half 1, minus 1 half 1, minus 1 half 1. I guess that's minus 1, right? That is also minus 1. But if I then write the primes in the other one, you can, there's a prime. So, anyway, so I have the determinant is minus 1 half minus lambda 1, negative 1 minus 1 half minus lambda is 0. So, yeah, that's good. So that gives me minus 1 half minus lambda, minus 1 half minus lambda, and then plus 1 is 0. So this one is in fact lambda plus 1 half, lambda plus 1 half. That's lambda plus 1 half squared. So that is lambda squared plus lambda plus 1 over 4 plus 1 and equal to 0. So that is lambda squared plus lambda plus 5 over 4 is 0. Let me check with the, yeah, correct. So lambda will be minus 1 plus minus square. Wow, that's what I had in mind. 1, okay. 1 minus 5 over 2. So that is minus 1 and plus minus 4 over 2. So that is minus 1 plus minus 2i over 2. So I have minus 1 half plus minus 2i. Sorry. Just divide plus minus i. Minus i. Okay. So let me write them here. Lambda 1 and 2 is minus 1 half plus minus i. Right. So let me erase this and find eigenvectors, and as I said, you just need one of them, one eigenvector. And so if I choose the first one, I will get minus 1 half. Well, let me write it again, times v1 minus 1, v2 is 0, that's the first row. And so minus 1 half minus 1 half plus I, v1 minus v2 is 0. So this is minus 1 half plus 1 half, that's 0. So I have I, v1 is v2. Okay, so if v1 is 1, v2 is I. So that is, now let me write it the way that I wanted that. So that is 1, 0 plus 0, 1, I, right? Okay, so that is 1, 0 plus 0, 1, I. So what is that matrix? 1, 0, 0, 1, right? So the a matrix is this, and the solution xy, remember, that was a constant c1 times this times, what's that, minus cosine, was beta. So let me write alpha is minus 1 half and beta is 1. So it is beta t, so it is t, sine t plus c2 of 1, 0, 0, 1, and sine t, cosine t, everything times e to the power minus 1 half t. Now, since this is a diagonal and it's 1, 1, Let's write it down more explicitly and take a look at the solutions. Okay, let me go through it again. So I found eigenvalues to be these two, and I just needed one of the eigenvectors, the one that goes with positive. Oh, gee, did I make a mistake here? I think I did. That's minus minus, right? Ah, minus. And therefore this is minus here, and I have a minus here, minus here, right? So that's the difference, right? Okay. So, yeah, I guess I should have chosen the minus one because always we have this thing. Unless we write it differently, but that's it. So let me erase this and try to write them down. The x is something like this. I have c1. This is just cosine, so I have minus c1 cosine t, and here I have plus c2 sine t e to power minus 1/2 t. And the y is c1 minus c1 sine t minus c2 cosine t e to power negative 1/2 t. Right? Well, let me double check with the book and see what the book has here. Oh, you can see that now. Yeah, okay, so cosine t, sine t, one of them is cosine t, sine t, the other one is minus sine t cosine t, minus sine t cosine t. Cosine, sine. Yeah, cosine sine is this, both positive. Well, I have negatives here, that's okay. I can just, and this one is sine minus cosine. So that is in fact the same thing, except with some, yeah, that is. So the book has, it's the same thing, except that this, if you choose the constant differently, you will get that solution. So in the book, it's something else. It's not something else, but it is, in fact, with negatives, say. And remember, the solution, if say y is the solution minus y, I mean this solution, the general solution, okay? Because it equals 0, so positive or negative doesn't make any difference. So, now let's look at this and see what I have here. This is in fact an interesting situation. Let me see. If I said that these two are in fact equation of motion, the x and y coordinates of a particle that is moving in xy plane, and t is say time. Let's see. Let me square both of them and add them. Okay, so let's square this and square this and add. When I square this one, well, this thing is common, so e to power negative 1/2 squared, t squared is just 2 times this, so I will get minus t, right? So that's e to power 1/2 power 2, and 2 times 1/2 is negative 1. So what happens inside? This one will be c1 squared cosine square t, c2 squared sine square t, plus 2 c1 c2 sine t cosine t. The second one is c1 squared sine square t plus C2 squared cosine squared T minus this time, no, this one's minus. This is minus, this is plus, 2 C1 C2 sine T cosine T. Okay? So, there's this one squared plus this one squared minus, there is a minus here, minus 2 C1 C2. This one is this one squared, twice this one times this one, which is just plus. Now when I add them, this cancels. What happens to this? This is sine squared plus cosine squared, so this one is C1 squared, and this one is simply C2 squared. So I have this interesting result that, let me erase this, I don't like this thing. So the interesting result is that x squared plus y squared is some constant e to power negative t. Okay. So the C1, C2 are some constants. It can be just anything. You can just put 1. Not 0. If you put 0, then you get nothing. So the C1, C2, one of the answers should be a non-zero number. So this is like a constant. Some constant e to power negative t. Okay, so if I write this in polar form, that is like r squared. So r squared is k e to power negative t. Or negative theta, that t can be theta because t is a parameter here. Remember in polar coordinates, you can choose that theta to be the parameter. So that gives me r is some constant, some k to the power 1/2 e to the power negative 1/2 t. Right? And let's assume that this constant is positive because this is square, so the constant is positive. And what is this? E to the power negative some constant times t. If you graph it, you can graph it on Wolfram or something, and you will see that it is a spiral like this. So the spiral, wherever you start, you can start at some small number because that's minus t. So if you start at say 10, that's basically 0. So start at like 0.0005 something. Anyway, so at very small number, so it's like well, you can say, okay, what happens at time t equal to 0? Okay, at t time equals 0, it is that this r equals, say, square root of k. So that is when theta is 0. So you start somewhere, right? So you start somewhere, let's say here, and then you continue, and you can see that r gets smaller and smaller, right? You can see that r gets smaller and smaller. So r gets smaller and smaller and smaller, and it's like you are approaching 0. And you can see that whatever t is, you never reach 0. That is an amazing observation of limit. Remember from Calc 1 that they always told you limit, you get closer and closer to something, you never reach it. This is in fact that situation. Just look, if you graph this thing and zoom, if I had the Mathematica here, I could show you that if I zoom, and you can see this thing still goes round, and never reaches point 0. Never. Just zoom it again. Round, and never reaches. It's like you're magnifying and you see the same thing. Whatever. But if you look at the scales on x and y axis, you see that now the scale is in 0.0000 something. But it looks like the same thing. I don't know. I might just plot this thing in Mathematica for several, and zoom it, and show you that that's just an amazing thing, an amazing, say, phenomena that happens. Okay, so if you can see that each one of them starts at some point, depending on the C1, C2, starts somewhere on the x-axis, and it's like positive, somewhere here, then it goes boom, 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 gets here. And there is no asymptote here. Remember in that case that we had real roots, there was an asymptote. There is no asymptote here. But the other one where, say, remember when the tangent lines were parallel to the x-axis or y-axis still are there. So if you write minus 1/2 x, the first one is plus y equals to 0, so that gives me y equals 1/2 x. On this line, x prime is 0, right? X prime 0 means that in the direction of x there is no velocity, so velocity is in the direction of y. Now, what is this line? This line is like this. I'm not too sure. It's saying that on this line, but this is not a nice picture. So on this line, it should be like this. I mean, the velocity should be in the direction of y, not x. So you can graph it on mathematical and also graph these two. So the second one, which is y prime, equals minus 1x minus 1/2 y equal to 0. That gives me y is negative 2x, right? Negative 2x, and that is something like this. So it should be, in fact, something here. And if I go to perpendicular, because these two directions are perpendicular. So on this one we have the y is 0, so it should be like this on this line. Y equals minus 2x. It should be in the direction of y, not direction of x. So it's parallel to yeah, the y is 0, so it's in the direction of x. This one is in the direction of x. Okay. So that is these two examples for you. Now the case that you have two in one eigenvector with multiplicity 2, I have written that down very carefully in those notes, and I used Abel's theorem by knowing that one of the solutions is, for example, e to power lambda t, and using Abel's theorem, you can find the other solution. I have given a proof of the Abel's theorem, but I don't. You can just skip that thing. That is like some technical, theorem about derivative of a matrix. So, I mean, derivative of a determinant, in fact, not to make the derivative of a determinant. So anyway, now I'm not going to discuss that. You can read that, and now next time I will discuss the non-homogeneous case, and I will discuss one method. There are two methods in the book, and I prefer the Laplace transform method. It is easy. I think it's easier and it's faster, and you don't have to do diagonalization and all those things. So see you next time.